this is where we look at system integration, i.e. we have a motor, we have a gearing system, right? So we have to determine the smallest diameter. So what we're going to do is we're going to determine the diameter of shaft AB. Okay. So we want to determine the smallest diameter that we can use. Okay. So what we are given down here is we are given that on shaft AB, right, the N or N, okay, number of revolution, we're going to rotate this at 880 revs per minute. And we have to deliver a power that is running at 30 kilowatt. Okay. So the formula we're going to apply for this relating to power is power is equal to 2 pi n t over 60. Okay. You guys probably have seen this formula before. It's so familiar. And I'm going to draw, okay, why this is critical, okay? So we are going to look at the characteristic of a motor. Okay. So what do I mean by characteristic? Okay, this is so those of you who are interested in cars, you have seen this before. So what we have is you have N, which is the number of revolution, and then you have power. You have power. So usually the higher the RPM, the greater the power, and you'll peak at a certain point and then you'll drop. Okay, so this is what you usually see. Okay, and then there's another graph. All right, there's another graph that you will also see in terms of torque. Okay, hold on, RPM and torque. So again, this is N. Okay. And this is the vertical scale. It's going to be the torque. So what you usually see is you have a peak point very quickly. And now this is for electric motor, okay, electric motor. Combustion engine can be different. Okay. The torque will go up very high, very quickly, and then it will go down. Okay. So if you look at torque, I'm trying to relate this to a car. Okay. The torque, how the torque will affect the performance of electric vehicle, for example. So the torque will influence the 0 to 100 kilometer per hour time. The higher the torque at an earlier time, okay, your 0 to 100 kilometers per hour will be shorter. Okay, right. So the higher the torque, will achieve shorter time to 100 kilometers per hour. Okay. Whereas the power will affect the maximum speed, okay, obtainable. Okay. So that's where if we were to compare a electric vehicle and one that's a regular combustion engine, usually the electric vehicle will tend to accelerate faster, right? But the maximum speed tend to be for in general, okay, before the combustion engine for this reason. Okay. Right. So coming back to here, right? Now, whenever we design a system, okay, we need to know this information. We need to know this information. So it all depends on how fast you want to run your motor. Okay. So just arbitrarily, okay, so for example, for this case, we're going to operate our system at this level. Okay, so we know that this is our operating boundaries. So we're going to design our shaft to put out 30 kilowatt. And then we're going to run at 480 RPM. Okay. Then we're going to use a formula to determine what is our torque. Okay. Okay. So this is a general point, just a point to make regarding the characteristic of the motor. So we also know that the power. So we are the other information we are given is the 30 kilowatt. Now the 30 kilowatt over here, right? So power input into system while the motor is equal to 30 kilowatt. Okay, 30 kilowatt is where we put in is the power input. Okay. Then we are also, if you look at the question, right? The machine connect to gears G and H. So this is gear G, right? So we have gear G and gear H, right? And one is to take off 20 kilowatt and the other one is 10 kilowatt. So power output from gear G is at 20 kilowatt. No, gear G. Yeah, gear G is 20 kilowatt. And power output from gear H, I think. Yep, gear H is equal to 10 kilowatt. Okay, so you realize that input is equal to 30 kilowatt and output is 10 plus by 20 kilowatt, and it's conservation of energy. Energy in, right? Energy in or power in must be equal to power out. Okay, so conservation of energy theory. Okay. So how is this information useful to us? Is we know that power, as written earlier, is equal to 2 pi nt over 60. So this formula is important because we can determine the torque. Okay, we can determine the torque acting on the gear. Okay, so now let me copy this image over here again so you can see. Right, power on the gear. So some of you will say, which gear? Right, which gear are we referring to? So the system of interest now is shaft AB. Yes or no? Shaft AB. I'm going to draw the centroid of shaft AB, or the neutral axis. Okay. So the shaft AB is of interest, right? Right. So whatever that is attached, immediately linked to shaft AB, right, are gears C, D, and E are attached to shaft AB, right? Gear C, D, and E. So the gears that we're interested are gears C, D, and E, not gears G and H, or the motor gear, right? I know this is common sense. I understand that, but I want you to I want to tell you, okay? So from here we can now determine our torque, right? We can determine our torque at gear what? At gear C, okay? At the torque at gear D, and the torque at gear E. Okay, so we can do that calculation. Okay, so the torque. So let me look at the torque at gear C. So we can start the calculation now. Okay, so we are going to determine the power for gear, or at gear C. Right, gear C. Power is equal to, so gear C is related to gear G, is 20 kilowatt. Okay, gear C is 20 kilowatt. Okay, so we apply the formula power is equal to 2 pi nt over 60. So the torque at gear C is equal to 20 times 10 to the power 3 multiplied by 60 divided by 2 pi, and the RPM is 480. Okay, so the torque at C, 20 power 3 times 60 by 2 divided by 480 is equal to 397.887 Newton meter. Okay. Then at gear D, and we look at gear D is connected to gear H, and gear H is taking away 10 kilowatt. Okay, so the same thing. So power equal 10 times 10 to the power 3 watt. Okay, so torque at D is equal to 10 times 10 to the power 3 multiplied by 60 divided by 2 pi 480. So it's half of 397. So it's equal to 198.944.